Hello everyone, this is Obaid Ahmad
And this is Sunil Kumar.
and we are here to present our video on the topic POH of charged air system, turbo superchargers and compressors in Jamalpur workshop.
So basically the charger system pressurizes the intake air, increasing its density, which results in increase in the mass of the intake air for the same volume of the cylinder, and it does so by using the energy of the exhaust air which is coming out through the chimney. What exactly is the need of this charger system? As we already know, for hauling maximum load, we are repeatedly trying to increase the resultant torque on the loco wheels, and it looks quite obvious that increasing fuel injected in the engine increases the torque. But if we look closely at this plot of torque per unit volume of air-fuel mixture versus the air-fuel ratio, and assume that we are already operating at this point, we find that increasing merely the quantity of fuel injected in the cylinder actually results in drop in the torque. But if we are simultaneously able to provide more mass of the air in the cylinder, we can maintain this point of high torque output per unit volume of air-fuel mixture.
Now let us take a look at the various parts of the charge air system. First up is the turbo supercharger, which is the main unit of charged air system. Next are the aftercooler and the V channel. The aftercooler is mounted on the power pack below turbo supercharger. It cools the high density air coming from the turbo supercharger. The V channel is part of the cylinder block itself, and it leads the air from the aftercooler to the cylinder through the inlet elbow. Then come the inlet elbow and the exhaust manifold. The inlet elbow, as explained before, provides the pathway to the cylinder, while the exhaust manifold carries the exhaust gases from the cylinder to the turbo supercharger. Now let us take a look at how the charge air system works. Initially, the intake air is sucked in by the impeller of the turbo supercharger through the air filter. This air is pressurized and sent to the aftercooler where it is cooled. Further, it passes through the V channel and the inlet elbow into the engine cylinder. The exhaust air from the cylinder is led to the turbine of the turbo supercharger. These high pressure exhaust gases rotate the turbine, which in turn rotate the impeller, sucking in the next batch of fresh air. Finally, the exhaust gases are ejected through the chimney and the cycle continues.
These are the various parts of the turbo supercharger. Turbo supercharger consists mainly of two casings, air discharge casing and the main casing. The gas inlet casing leads the exhaust gases to the nozzle ring, which converts its pressure energy into the kinetic energy. This high-speed gas strikes turbine in the main casing, causing it to rotate. This rotary motion is transferred to the impeller in the air discharge casing through the rotor shaft, and thus sucks the fresh air in through air inlet casing. The combined effect of the impeller and diffuser increases the pressure of the air, making it dense. Finally, this air is fed to the aftercooler through this opening. This is the flowchart of POH process of the charge air system. Various components of the charge air system are dismantled and sent to their respective sections for the POH. After POH, they are assembled in the power pack section, and finally, turbo rundown test is done during the load box testing. Now we will take a look at POH of turbo supercharger. Firstly, it is dismantled and all parts are cleaned. After this, all parts of the turbo supercharger are inspected using various tests like dye penetrant test and pressure test. Then the various defects found in the testing stage are repaired. This table shows the main defects in various parts of the supercharger and the repairs done. After repairing the rotor assembly, balancing is done to remove any imbalance which can cause excessive vibration and stress while rotating. After repairing, all parts of the turbo supercharger are assembled and turbo rundown test is done during the load box testing. In this testing, engine is made to run for some time and then switched off. After switching off, the time in which the rotor assembly comes to rest is noted. Ideally, it should be between 90 to 120 seconds. In the POH of the aftercooler, first, the housing is removed and the radiator is cleaned with trisodium phosphate. The aftercooler is disassembled and the tubes of the radiator are gauzed using a rod. After this, hydraulic test of the radiator is done and the cracked tubes are made dummy by sealing both their ends. According to the RDSO, a maximum of 5% of the tubes can be made dummy. The inlet elbow is visually checked and the gasket seat is filled with stone. The exhaust manifold is dipped in caustic soda for 24 hours and then dye penetrant test is done. Cracks, if found any, are welded. Finally, all these parts are assembled in the power pack section.
Now let's move on to compressors. A compressor is a device that converts power into potential energy stored in the form of pressurized air. In a loco, it is used to compress air for various uses like braking, blowing horn, and even operating the wipers. Clearly, this is one component that can't be done without. The currently used model is RR80101 as shown in the figure. It has specially been designed to meet the high volume of air requirements with moderate pressure to be used in locos. It is a two-stage reciprocating W-type compressor with intercooler and aftercooler. This figure shows the operation of the aforementioned compressor. Due to movement of piston in the two low-pressure cylinders, air is sucked in through the air intake strainers. The compressed air from the cylinders is led to the intercooler where it is cooled and then fed to the high-pressure cylinder through safety valves where it is further compressed and then finally cooled again in the aftercooler. Thereon, it is fed to the main reservoir for further operations. Coming on to the various parts of compressors. First up are cylinders. On the left is the low pressure cylinder, while on the right is the high pressure cylinder. Cylinder heads and valves. This compressor is equipped with 3 cylinder heads. The valves are individual disc type loaded with springs, operated due to the differential pressure between the upstream and downstream pressure. Crankshaft and connecting rods. Crankshaft is made of special alloy forged steel so that deflection is minimized and the wear is reduced. A fan is mounted on the one end. The connecting rods are mounted over the crank pin adjacent to one another. Compressor pistons. The low pressure pistons are made of aluminium and elliptically ground on the outer diameter. The high pressure piston is cast iron. Main bearing. 2 double row ball bearings are assembled on either side of the crankshaft, which takes the misalignment in geometrical tolerance and operation. End cover. End cover is made of cast iron, which has more stiffness and deflection minimized, which enables the rigidity. Oil level gauge. It indicates the oil level in the crankcase. Crankcase. Crankcase is the main component of the compressor, which houses the crankshaft, connecting rods, lube oil pump, etc. Intercooler. The intercooler reduces the temperature of the compressed air, leaving the first stage prior to entering the second stage in order to improve the overall thermodynamic efficiency of the system. Aftercooler. The aftercooler assembly reduces the outlet temperature. It is made with external finned copper pipes. Suction unloader valve. The unloader assemblies are a part of compression system located over the suction valve. It is pneumatically operated when the system pressure reaches roughly 10 kg per centimeter squared. Crankcase breather valve. It is shown in the image below. The breather assembly is mounted on the crankcase. It operates as a check valve to provide a partial crankcase vacuum during normal operation of the compressor and to discharge air displaced in the crankcase during the compression process. The compressor lubricating system is piloted by the gear drive oil pump. The oil pump circulates the oil under pressure. Drive is taken from the crankshaft by means of a set of gears. A primary oil filter, which faces the inner side of the crankcase bottom, filters the oil to prevent the ingress of external agents like dust and other solid particles from entering into the pump and the lubricating system. The filtered oil passes through the groove to the distributing ring. Through the distributing ring, the lubricating oil flows to each crank pin in the crankshaft through the oil holes drilled in it. The oil lubricates the inner bearings of the connecting rods through the groove provided and the needle roller bearing and gungeon pin at small end through the hole drilled in the connecting rods. This is the flowchart of the POH process of the compressor. The compressor is dismantled and various parts are sent to the respective sections where they are cleaned, inspected and repaired. The compressor is then assembled, tested and finally mounted on the loco. Now let us take a detailed look on the POH of a compressor. Firstly, the compressor is disassembled in the compressor section itself. Then on, the parts are cleaned using K-oil and pressurized air. All the parts are visually inspected and various tests are conducted on different parts, like Ziegler test on piston and cylinder heads, Magna flux test on crankshaft, and hydraulic test on intercooler and aftercooler. Components are then repaired or replaced accordingly. Finally, all parts are assembled. The compressor is mounted on test bench and its performance is carefully monitored for any irregularities. Thanks for watching. Have a nice day.